Hi everyone, welcome to our last webinar in lighting. Today we will have a very nice presentation from Leos Kukacka from Czechia. But before introducing Leos, I'd like to welcome everyone and to say that these webinars are being organized by our lighting research group from the Federal University of Santa Maria, together with the Federal University of Juiz de Fora. Besides, we have the support of the IEEE student branch from the Federal University of Santa Maria. And you can find in the chat the link of a form to be filled. If you fill this form, you can receive the certificate of attendance of this webinar if you are interested. First, I'd like to invite the electrical engineer Vicente Scopacasa, that he is also a lighting engineer from São Paulo, to help me to moderate this webinar. So welcome, Vicente.
Okay, Marco, good afternoon to you, to our guest, Leos, and all the people that are, participating in this webinar. Thanks for the invitation. It's a real nice subject. I'm pretty much involved on it also. Is one of the topics I am, investing some of my time. And I'm here to participate and learn a little bit more about Flickr. Thank you very much for the invitation once again.
Thank you very much, Vicente. And now I'd like to introduce Leos Kukacka. Leos received his Ph.D. at the Technical University of Liberec in Czechia, and also from the University of Paul Sabatier in Toulouse, France in 2018. In 2020, he absolved a postdoc internship at the Technical University of Dresden in Germany, and he is now assistant professor at the Technical University of Liberec in the Faculty of Mechatronics, Informatics and Engineering Studies. His main field of research is the quality of electric power, flicker, and its perception. Leos is member of IEEE since 2014 and member of the Czech Society for Lighting since 2019. So, Leos, thank you very much for presenting this webinar for us, and be very welcome to this webinar.
Thank you for a nice introduction. Hello, everybody. I'm happy that you participate in this webinar. For my today's talk, I prepared a few slides as an introduction into the field of measuring and analyzing flicker and related phenomena. We will have a closer look at the phenomena, what are they? Then I will show you ways how to measure and quantify the flicker. We will have a look at the way LED drivers act in producing flicker. Lastly, I will briefly mention a few ideas that are worthy of more investigation in this field. So first, let us define what will be the subject of our talk today. What is flicker? What are the related phenomena? Here I put down a few definitions of flicker. Let's have a look at them. The IEEE Society defines flicker as the impression of unsteadiness of visual sensation induced by light stimulus whose luminance or spectral distribution fluctuates with time. Please note here that there is no notion of frequency or environment, meaning that also some phenomena related to higher, normally invisible frequencies may be called flicker. The CIE Society, on the other hand, makes a difference between flicker and the so-called TLAs, temporal light artifacts. In the definition of the flicker, it is explicitly stated that flicker is bound to static observers in a static environment. This restricts the flicker to fluctuation frequencies below approximately 60 Hz, as I will explain later on. On the other hand, temporal light artifacts are phenomena caused by fluctuations at arbitrary frequencies, meaning that also high frequencies can be made visible by dynamic, moving environment. Similarly, the IEEE makes difference between visible flicker and invisible flicker, with the distinction being strictly the frequency of the fluctuations. So in my talk, I will stick with the CIE framework, which seems to me to be the most complete. So allow me at this moment to talk a little more on the definition. So we have the so-called luminance flicker, which is a fluctuation of the luminous flux. Or we can have so-called heterochromatic flicker. This is when the spectrum of the light is changing, as also mentioned in the definitions, while the total luminous flux remains constant. Normally, or very often, we get a combination of both. Take, for example, the incandescent bulb. You have the tungsten filament heated to a certain temperature, emanating light with spectral distribution given by the Planck law. When the voltage or the current changes, so does the filament temperature, and we get a change in both the luminous flux and the spectral distribution. With LEDs, we also have chromatic flicker, because LEDs change the wavelength of the primary emission independently on the supply current. Things are a little more complicated with white LEDs using phosphor, because the secondary emission produced by the phosphor remains stable as far as the spectrum is concerned. But the phosphor is not always, but often slower than the LED itself, and may keep emanating light when the primary emission is dimmed for a brief moment. As also mentioned in the definitions, we can have flicker in static conditions, in which case only low frequencies up to a certain limit, around approximately 50 or 60 Hz, are relevant. Basically, you do not care about frequencies higher than that in static conditions because you cannot see them. With dynamic conditions, you have to take into account also higher frequencies. Higher up to what? Well, that depends on the conditions. Also, depending on the conditions, we can have several families of phenomena related to high-frequency flux fluctuations. Those are the temporal light artifacts mentioned in the definitions earlier. So when the light source is moving, you can have phenomena such as the phantom array effect. That's when, for example, you are driving late in the night and the backlights of the car in front of you are flickering at high frequency. You may notice the light to appear like dancing around. This may appear disturbing or even confusing, and so dangerous, particularly when driving, right? When the illuminated object is moving, you can have stroboscopic effect, which is depicted here on this picture, the one with the screwdriver. The moving object appears to be jumping between stable positions. Similarly, a rotating mechanism may appear to move more slowly or in reverse or even stationary. This is the famous coach wheel effect that happens on old movies. Finally, even when your surrounding is otherwise static, you may experience flicker sensation from high frequency fluctuations during rapid eye movements, or saccades, as they are called. It may not seem so, but the angular velocity of your eye during these movements can be really high. So in general, research of flicker is an interdisciplinary field, bringing together knowledge from ophthalmology, photometry, power electronics, and also electromagnetic compatibility and power quality monitoring. At this moment, already it should be apparent why we should care about flicker and all related phenomena. So let me just summarize. The TLAs, the temporal light artifacts, I'm going to call them just TLAs. They can be dangerous, creating conditions for possible injury or car crash. Visible flicker can be simply annoying or irritating, but it can also cause headaches, dizziness, migraines. In the worst case, it can also cause epileptic seizure in people who are sensitive to it. There is a well-documented example from Japan. Sometime in the 1990s, there was Pokemon series on the TV. Recall the TVs of that era. Those were the cathode ray tubes flickering by themselves a lot, significantly. And in one of the episodes, there was a scene lasting several seconds, and there was blue and red light switching rapidly at 12 hertz or so. And the scene took like 6 seconds. And unfortunately, afterwards, throughout Japan, hundreds of kids were hospitalized with epileptic seizure caused by this scene. So human health and safety are the largest concerns, but flicker can be also problematic for cameras and machine vision, causing artifacts on videos and photos. Not a big topic today, but in future, autonomous robots will have to be able to deal with flickering lights. So now let us talk about the mechanisms that are the cause of all those phenomena. The cause number one of visible flicker are the network disturbances. Imagine you have a network here on this diagram represented by a voltage source and network impedance. At the customer side, you have a time varying load. That can be a microwave, an oven, etc. And the changes in current consumption of this load result in voltage drops over the network impedance. And in this way, they affect also the lighting system because the voltage changes. Electromagnetic compatibility standards bind appliances to such current consumption patterns that do not cause significant visible flicker, at least with incandescent lamps. Second significant cause of flicker is the AC nature of the voltage supply itself. On this slide, you see several pictures. So you see the main supply voltage. In this case, it's 230 volts, 50 hertz. On the upper figure, to the right, you see an estimate of what the luminous flux of an incandescent lamp is. This is not a measurement. This is from a model of an incandescent lamp. You see that the light modulation is not severe. It falls to roughly 80%. So it's not severe, but it exists. The light does not go completely dark during the cycle due to thermal inertia of the filament. The lower figure shows what could happen in the worst case with LEDs and what is in fact happening in the cheapest LEDs available in the market. You see that the light goes completely off during the cycle. Pulse width modulation used as a way to control the output of the LED also has to be used with care. The LED current should be smoothed using an inductor. Otherwise, the effect of flicker can be severe, as you can see in the picture on the right. This looks easy, and one would think that lamp manufacturers recognize this, but this is not the case, especially with cheap lights, cheap lamps. For example, in my car, the headlights that are used during the day, they flicker a lot due to this PWM. Next possible cause of flicker is improper installation, particularly when people use retrofit LED lamps in combination with phase cut dimmers. The phase cut dimmers are designed to control incandescent lamps, and they may cause trouble with LEDs that are not accommodated to be used with phase cut dimmers. Aging is an issue for flicker, especially with fluorescent tubes, but not with LEDs. We probably do not need to discuss this in deeper detail. What is not usually a cause of flicker and related trouble is data transmission via visible light, so-called Li-Fi. To have sufficient transmission rate, the frequencies that are used have to be really high, safely above the relevant band. If it's megahertz or gigahertz, we don't have to be concerned. That's safe. So now we went through the basics. We know what flicker is and how it is caused. Before we move on to how flicker is measured, let's have a look at the border between visible and invisible flicker, the critical flicker frequency, or also called flicker fusion frequency. It's usually abbreviated CFF. And also, let's have a look at other phenomena related to flicker and human vision. The CFF is defined as the frequency beyond which people stop perceiving visible flicker. As such, it depends on many factors, such as the observer's weariness, shape of the waveform, or the light's luminance, the brightness level. This is called the Ferry-Porter law. The CFF changes logarithmically with the luminance level. And background white noise, or auditory noise, was, for example, shown to increase the CFF in several studies. Whether this is due to some neural connection in brain between centers for hearing and vision, or just because higher noise level increases the person's alertness, that's not known. There is definitely a gap for future research here to explore in more detail the link between auditory stimuli and the CFF, or flicker perception in general, not just the CFF. Now, it would be a mistake to view the CFF as a single frequency. Rather, we have a transient zone where the observer's ability to differentiate between fluctuating and stable light source decreases. Below the CFF, not only that the observer perceives flicker, but also the luminance appears brighter than it actually is. This is called the Brücke-Bartley effect. This effect is reported to be strongest at 10 Hz. On the other hand, above the CFF, the light appears to be averaged out as far as the brightness or luminance is concerned. This is called the Talbot Plateau law. As a side note, for those of you who are interested, the Talbot Plateau law was formulated in the 19th century using a stable light source and a slit, where the rising slope of the light pulses produced by the slit was relatively slow. Because LEDs can be much faster than that, there came an idea in the recent decades to revise the Talbot Plateau law using pulses with very steep slopes. And indeed, there are several studies available that claim to disprove the Talbot Plateau law. The results are unfortunately somewhat inconsistent. Basically, each study reports slightly different results. At my university, together with Laboratoire Laplace in Toulouse, we built a setup to allow verifying the Talbot Plateau law to join the long series of the preceding studies. Recently, we had the first results, and Unfortunately, they do not offer sufficient evidence to disprove the law, but we found large variance in the data, and we must yet focus on decreasing the variance before we go further. So anyway, back to our topic. The fluctuation frequencies that are relevant for TLAs are roughly up to 2 or 3 kilohertz, unless one finds himself in an environment with very, very fast-moving objects. Now, let's have a look at how flicker is measured. Historically, with the incandescent lamps being the dominant light source in the first half of the 20th century, practically the only cause of flicker trouble were the network disturbances. The most significant disturbing device that is discussed in literature were the arc furnaces, big, powerful devices for melting metal. This led to extensive research of flicker perception between 1950s and 1970s. To make things a little more easier, a double filament 60-watt incandescent lamp was chosen as a reference lamp, and all considerations were related to this reference lamp. This research then led to the definition of the flicker meter in 1980s, also sometimes called the IEEE flicker meter or voltage flicker meter. The idea with the voltage flicker meter is to sample the mains voltage, model the response of the incandescent lamp and the way humans perceive flicker, and calculate a special quantity which relates to irritation of human observers. Of course, nobody really uses incandescent lamps these days, but this metric is far from outdated. Since its publication, this algorithm became an important tool to monitor the quality of voltage in the distribution network. As I said earlier, appliances are bound to have such current consumption patterns to not cause significant flicker with respect to this flicker meter. So let us go briefly through the algorithm. It has some very useful properties that are worth of examining. Well, block 1 is just normalization of the input voltage. Block 2 is already a part of the model of the incandescent lamp. By squaring the normalized voltage, we obtain normalized instantaneous power consumed by the incandescent lamp. Block 3 then consists of several filters. These filters together constitute a special transfer function that models together the frequency response of the incandescent lamp and that of human eye. The magnitude response of block 3 is shown in the picture. I chose a linear plot of the magnitude response deliberately. The peak response is at 8.8 Hertz, and you can see the response is practically zero above the CFF. Here we have the zone where the CFF usually is, between 40 and 60 Hertz. It is important to realize that this is a single transfer function that reflects both the incandescent lamp and eye. This is because the experiments were done with people observing the reference incandescent lamp, and it was not deemed important to make difference between which part of the response is caused by the lamp, which part by the eye. Block 4 is usually referred to as a model of brain. This is a little inaccurate, but it does reflect the way our brain tends to combine two consecutive stimuli into a single perception. Output of block 4 is the instantaneous flicker, usually denoted as P-inst. This is a quantity scaled so that the flicker visibility threshold is at p-inst being 1. And then block 5 is a statistical evaluation of the p-inst in a given time interval. That's usually 10 minutes. The signal samples are sorted, specific quantiles are calculated and combined into a single number, the flicker severity index, also denoted as PST. This number is scaled so that the PST being 1 means that roughly 50% of observers would be irritated by flicker. It is also linear, so twice the modulation depth of the voltage means twice the PST. Now, there is a lesson to be learned from this approach. Notice that the evaluation of the flicker happens continuously in time domain. You do not need to perform Fourier transform and bother yourself with spectral leakage, integer number of fundamental periods, etc. The algorithm can be implemented in a device and work by itself without anybody's involvement. Oh, sorry. Okay, this is the right slide. To overcome the drawback of being restricted to incandescent lamps, a luminous flicker meter was also defined in 1915. The idea now is to sample directly the luminous flux independently on the light source it is coming from, and then continue the evaluation in the same way. You see in the picture that block 2 is completely removed, and block 3 is adapted to not include the reference lamp response. For this, an extra model of the reference lamp was required to construct, and it was then subtracted or divided out from the filter transfer function. Consequently, as you can see, the response of block 3 is slightly different, is the red line. The peak response is shifted to 10 Hz. The rest of the evaluation chain then remains the same. The block 4 and the block 5 is the same. And the p-inst and PST are also the same. Now, I have a little task for you. I would like you to remember this response curve, the shape of the transfer function. We are going to see it later on in my presentation. So, with incandescent lamps, the phenomena related to high frequencies were not really relevant. Things started changing with the fluorescence, and then the rules of the game were completely changed by LEDs, as I will explain later on. LEDs can be really fast. Now, let's have a look at how high frequency phenomena can be quantified. Traditionally, modulation depth of the luminous flux was evaluated using the Michelson contrast, taking into account the maximum and minimum of the evaluated waveform. This approach was standardized in the IEEE 1789 standard, released in 2015 as the percent flicker. It is a very simple approach. Similarly, the flicker index is calculated as the ratio of the area 1, as shown here in the picture, and the total area below the curve. The trouble with these two metrics, the percent flicker and the flicker index, is that they are not related to human vision at all. They just describe the waveform. Shortly after the IEEE 1789, in 2016, the CIE released a document defining the stroboscopic effect visibility measure, SVM. This is a step forward, as this metric is scaled so that SVM being 1 is the visibility threshold, That means that 50% of people would observe stroboscopic effect. To calculate SVM, you need to perform Fourier transform and weight each frequency component with a special weighting function. Shown here in this picture is a SVM threshold function, and the weighting function would be the inverse of this threshold function. Similar to the SVM, there is also defined the phantom array effect visibility measure. The difference is just difference weighting function, but the principle of the calculation is the same. As I said, these metrics are a step forward because they are related to human vision and human perception of flicker and of these phenomena. But still some of the drawbacks remain. Important fact here is that all metrics assume periodicity. Basically, this restricts the evaluation to laboratory conditions with ideal supply, free of disturbances. This way, one can assess behavior of a single lamp, but the assessment of environments lit by multiple lamps, each flickering may be at slightly different frequency, supplied from public grid with distortion. That's complicated. And you have to be very careful when doing the signal processing to evaluate those metrics. Otherwise, you can have bias, you can have spectral leakage, etc. Now, let us move from the flicker measurement to challenges for lighting systems. Today, when we talk about lighting, well, we talk about LEDs, right? LEDs are very efficient and very fast sources of light with very wide possibilities. Because we are concerned with flicker at this moment, it is important for us that the luminous flux produced by an LED is very closely related to the LED current. Because they are very fast, the LEDs will reproduce any supply current fluctuation to luminous flux fluctuation. This is both good and bad for us. Good news is that we can have control over the stability of the luminous flux. The bad news is that we must have control over the stability of the luminous flux. This is why LED lamps need a driver, an electronic circuit that's responsible for proper supply of the LED. So when we are concerned with flicker of LEDs, we are interested in the driver and its properties. LED drivers must deal both with visible flicker and high-frequency TLAs. As for the TLAs, because we already know that the culprit is either the driver itself or simply the AC supply, driver manufacturers have now sufficient tools to determine whether the driver will be safe or not. Thanks to the IEEE 1789 standards, we have limits for maximum modulation of the luminous flux depending on the frequency. With PWM, the solution is to make sure to smooth out the PWM or move the frequency beyond the relevant band. I'm aware that there are more factors for choosing the PWM frequency, but this is from the perspective of the interaction with humans. Things are a little more complicated with immunity to electromagnetic interference and network disturbances. Here I prepared 3 different pictures to demonstrate the issue. In the left is flicker response of an incandescent lamp supplied by DC voltage. The DC voltage was sinusoidally modulated and always at a single frequency. And for each frequency, the luminous flicker meter was used to establish the Ph.D, that the visible flicker severity index. At this moment, it's not important to look at the values on the ordinate. What I want to show you is the shape of the response. Remember the sensitivity function for visible flicker? This is why frequencies above 50 Hz are not relevant. This is incandescent lamp supplied by DC. Okay. The middle picture is incandescent lamp supplied by 50 Hz AC voltage. Again, each time the supply was modulated at a single frequency and the flicker severity index was calculated from the luminous flux. You can see now that the pattern is changed. What's relevant for flicker is the product of the interaction between the fundamental supply frequency and the disturbance. This means that in AC grids, the flicker relevant frequencies are up to twice the fundamental frequency. This is also a point where we have to start making difference between the disturbing interharmonic frequency and the modulation product in the visible range, which is here denoted as Fvis. The reason behind this phenomenon is that the luminous flux from incandescent lamp is related to the consumed instantaneous electric power, and that in turn is proportional to the square of the supply voltage. This behavior of incandescent lamp is also why we have electromagnetic compatibility limits for subharmonics and interharmonics up to twice the fundamental frequency, but not above. The limits are defined so that the extra disturbing components should not cause Pst larger than 1 with an incandescent lamp, with the voltage-based flicker meter. The third picture in the right shows the same experiment and the same data with an LED and a driver. Can you see the difference? Again, ignore the absolute values of the Pst. This is a laboratory experiment. What I'm showing you here is the mechanism. With LEDs, interharmonics of much higher frequencies can cause visible flicker under static conditions for a static observer. The culprit here is the diode rectifier at the input of the driver. By the rectification, we obtain voltage waveform that is rich in harmonics. The disturbances are capable of interacting with the higher harmonics and getting translated or aliased to the frequency band below 50 Hz and causing visible flicker. This is a special issue with ripple control messages that are used for load management in distribution networks. Those messages are usually transmitted at an interharmonic frequency between 100 and 1600 Hz. For example, in my country, one of the common frequencies is 216.7 Hz. And I know from my own personal experience that those messages truly do cause visible flicker in static conditions at a very disturbing level with LEDs. So you see that it is important to study the behavior of the LED driver at higher frequencies, even when one is concerned with the visible flicker. To sum up, in LEDs, one has to deal with the high frequency fluctuations to avoid TLAs. But after that, one has to pay close attention to the driver's immunity to network side disturbances in wideband of frequencies. Making similar analysis, as shown here in the picture, is very helpful on that. But still, here in the picture that's shown, the shape of the flicker sensitive function kind of obscures the response of the driver itself. What we see is the shape of the flicker sensitivity function, as I shown you earlier, but the pattern that is behind that, caused by the driver, is somewhat hidden. So to study driver properties, it would be better to not evaluate the Pst with its sensitivity function, but rather unmask the natural response of the driver itself. This is why we usually work with the gain factor. The gain factor is the ratio of the relative magnitude of the supply voltage disturbance at a given frequency and the relative magnitude of the fluctuation at the translated visible frequency that's below 50 Hertz. It shows the potential of the driver to translate higher frequencies to visible band and thus cause flicker, visible flicker. In the graph to the left, you see several typical patterns that were identified in recent literature for 8 typical driver topologies. I've drawn simplified diagrams for each of the 8 driver classes. Basically, there are passive drivers out there that have no current control at all. Those usually have capacitive divider, that's class A. Active drivers can have constant current control, class 2, or they have switched mode power converters. The power converter can either be open loop with fixed switch ratio, that's class 3, or closed loop with feedback from the output, current feedback from the output, this is class 4. Some drivers are equipped with active power factor correction circuits. Those circuits do not have a smoothing capacitor at the input, or it's very, very small, and the converter is designed to more network-friendly current consumption. But in this case, the stability of the output is compromised. We're talking about class 5. In class 6 drivers, the converter does have active power factor correction, but it is rather optimized for stable output current. Classes 7 and 8 are two-stage drivers, meaning that they have a DC-DC converter serving solely as active power factor correction unit, and a second DC-DC converter used for stabilizing the output. The difference between 7 and 8 is whether the second stage drivers are open loop with fixed switch duty ratio, or whether they are closed loop with a feedback from the output. Those two-stage drivers are almost always found in external drivers, not in retrofit LED lamps. So I went just briefly through these driver classes identified in literature to demonstrate that each feature built in the driver affects the driver's gain factor pattern as shown here in the graph. But these are just typical curves for each class. Of course, in each driver, there is a number of parameters that affect the gain factor curves as well. Is the capacity of the capacitors, well, related to the rated power of the driver? Is the switching frequency, is the inductor, is the properties of the feedback controller, etc. The classes in general constitute just a topology of the driver, not the actual implementation. It's interesting to have a look at the gain factor curves and compare them with the incandescent lamp. The reference 60-watt incandescent lamp would have a gain factor of approximately 3,6. That's a lot higher, but only close to 50 Hertz and falling rapidly on both sides. And above 100 Hertz, the gain factor of incandescent lamp is 0. As I already showed you in the previous slide, above 100 Hertz, the incandescent lamp is insensitive. This is also why we have no electromagnetic compatibility limits on higher interharmonics, because the incandescent lamps are insensitive to those, but LEDs are, unless you have really good and expensive two-stage topology driver. So the lesson of my today's talk should be that, of course, the LEDs should not exhibit high frequency fluctuations on the nominal supply. The driver designers should take care of that, but also it is very important to make the drivers insensitive to network disturbances. And as always, this is about finding the compromise between quality and price. It's not that people would not know how to make good quality driver without Flickr. It's because it's expensive. And for some lamps, the issue is also limited room for the driver and heat dissipation. But there's also lack of legislation. Okay, the current challenges for research on Flickr can be, at least in my view, can be sorted into 3 branches. Branch A, deeper research on how people perceive Flickr. Is Flickr perception related to background noise? If yes, is it an issue for loud environments like factories? Or is the Flickr perception changed in mesopic and scotopic conditions? This is especially important for designing public lighting. We know that the critical Flickr frequency is lower, that's the Ferry-Porter law, yes. But what about the sensitivity curve in those conditions? Branch B, enhancing and updating the standing Flickr metrics. We already know that the block 5 of the Flickr meter was optimized with respect to arc furnaces. These are not an issue in modern grids. We rather have different disturbance patterns in modern grids. In 2014, there was published a proposal suggesting to change the way PST is calculated in the Flickr meter. My most recent research is focused on whether this proposed change is in accordance with the way humans perceive Flickr. My colleagues from Technical University in Dresden and Brno University in Technology and we designed a set of experiments to verify that. The results are now in peer review process. Another branch of research, well, we already have the Luminous Flickr meter, which is free from modeling any kind of lamp. It would be really nice if we could implant a model of an LED into this Flickr meter, and this way obtain an LED-based Flickr meter. But which LED should we model? Yes. With my colleague from Brno University of Technology, Professor Jiří Drápela, we work on creating a suitable model for each LED driver class. So far, we created models for classes 4 and 7, which are quite common, but this project is not finished yet. Further, a nice idea could also be to define the SVM in such a way that would allow evaluation of the SVM, the stroboscopic effect visibility measure, in temporal domain, and remove the limiting need for periodic waveform, just like the Flickr meters work. And lastly, branch C, well, it would be nice to have more clear standards. Still, the standards that we have are mostly just recommended practices or technical reports. There is no legislation that would enforce putting Flickr-related information on the label of the lamps that the customers buy. And frankly, it's not clear what this information should be like. We also do not have limits for higher orders of interharmonics, and we do not have minimal requirements on the driver immunity to network disturbances. Okay, this is all from my side. Let me just slide quickly through the list of literature references. This talk is on record, so if there is some information you might like to look up, you can just pause the video later and have a look. And thank you for your attention. I hope I will be able to answer your questions if you have some.
Thank you, Leos. Thank you very much for your nice presentation. This is a very interesting topic in lighting, since the flicker is directly related to the LED driver development, mainly in the case of the capacitor design, because we know that the electrolytic capacitor is the weakest point of our LED driver, and it is directly related to the flicker. So now we have time for some questions. I'd like to ask from the audience to send any question or comment through the chat, so we can read it to Leos. But while we don't have other questions, we will make our questions here, me and Vicente. So Vicente, I think that you could start with your comments and questions to Leos.
Okay. Well, Asha, very nice presentation. Congratulations. Very deep, very technical, very good. I really appreciate that. Actually, I have prepared some questions, but you quite answer all of them. But there is one specific question: do you believe that flicker control is applicable only when the flicker source is the only light source in the ambient?
Well, I think that these are two different things. One thing is to analyze a lamp, a single lamp when it is designed and its properties, and another thing is analyzing flicker in a specific environment when there are multiple light sources together, illuminating some task that people are working on, some machinery. That's something different, and we should be able to measure flicker also in these environments where there are multiple light sources together.
Oh, okay. Well, I have another one. You mentioned something that I never heard before, the heterochromatic, and I didn't quite understand when you mentioned that. Well, this is a change of the light spectrum, right?
Yes.
And you said that you mentioned something regarding the phosphor. Of course, we are talking about phosphor converted LEDs, right? You mentioned a difference between the phosphor portion of the spectrum and the blue plump also. Can you explain better this, please?
Yes. So phosphor-based white LEDs have two families of wavelengths that they emit at. One family is the natural primary emission from the junction, and then we have the secondary emission from the phosphor. And when we change the current through the LED, the primary emission shifts slightly depending on the current, but the secondary emission from the phosphor doesn't. So this may cause changes in the spectrum, and then we can have phosphors that have fast temporal response, that are fast, or some phosphors are slower. And when we have fast flickering LED, the primary emission may go down, while the secondary emission from the phosphor is still emanating some light. So this can further enhance the changes in the spectrum.
Oh, okay, I see. Thank you. Thank you very much. Marco, you have another question?
Yes, we have some comments and questions from the audience. Leos, we have here a comment from Pascal. Could you comment about it? He says that one point worth emphasizing on flicker index and flicker percent. Analog noise is quite annoying as the computation do not take it into account.
Yes. Thank you, Pascal, for asking. Analog noise is problematic with this metric, and for example, with the percent flicker, you measure the maximum and the minimum of the waveform. But with analog noise, the maximum can be overestimated and the minimum can be underestimated. So you have a bias in the metric because the metric will seem always somewhat higher to you than it actually is. So this is something that should be taken into account, especially when the acquisition noise is high with devices like oscilloscopes.
Okay, Leos. We have another question from Guillermo Osorio. Guillermo is from Colombia. He's asking how you can get a prediction lifetime of an LED light source when you have a flicker phenomenon.
Well, as for the high frequency flickering, that will probably have something to do with aging of the LEDs, and I know very little about that. I'm afraid I cannot answer that. As for the network disturbances, it's maybe possible that the network disturbances may cause overheating of the capacitors. As you mentioned, the capacitors are problematic in LED drivers, but honestly, I do not know much about lifetime of LEDs and aging. That's not my field.
Well, maybe Vicente could comment about it. Vicente, you have a lot of experience in LEDs. Do you know anything related to the flicker and the lifetime of LEDs?
Well, the most common way to verify lifetime or lumen maintenance of the LED is the IES LM80. And in this document, they never touch the flicker subject. So, in my understanding, flicker has nothing to do with the lumen maintenance of the LED. No, it's more a kind of the phosphor property because LEDs with higher CCT using a different phosphor, they have of course a different lumen maintenance compared to the warm white LEDs, which use a different formula of phosphor. So I would say that, in my opinion, and based on the most common way to measure lumen maintenance today, which is the IES LM80, that I don't see any relation with flicker, in my opinion.
Yes, I think that is more related to the lifetime of the LED driver. LED driver is a separate. What I just mentioned is related to the LED, the diode, right? Yes. Yeah, I'm not considering. Of course, if you think about the whole system, I think the driver is more problematic than the LED in terms of lumen maintenance of the whole system. Absolutely. Vicente, do you have other questions to Leos? Actually, I have one final question. Here in Brazil, the frequency of the network is 60 hertz, right? So every time I make a flicker measurement, it's always 120 hertz, which is the double, right? So in this frequency, what am I really measuring? Flicker or stroboscopic effect?
So at 120 hertz, it shouldn't be visible in static conditions. So it's the stroboscopic effect.
Yeah, right. Okay. Yeah, I had these doubts. So makes sense. Yeah, to me makes sense. It's not flicker; it's stroboscopic effect at this frequency, right?
Yes. Anything above 50 or 60 hertz of the fluctuation of the light is is rather related to the temporal light artifacts,
Mm-hmm.
such as the stroboscopic effect.
Okay, thank you.
Leos, I have one question for you. I'd like to hear your opinion about Flickr in different situations. For example, street lighting, I think that Flickr is not so important, for example, compared to office lighting or residential lighting. What is your opinion, and also if you have some knowledge about different limits for Flickr in different applications? For example, mainly comparing public lighting and interior lighting.
Well, firstly, I'm not very much familiar with any standards on public lighting. But in my opinion, what's important for public lighting is the TLA, the temporal light artifacts, particularly the stroboscopic effect. It can be very dangerous, as I said, especially when driving. You need to move your head fast, looking left, looking right, and if there is a flickering light out there, it make you feel confused when you are driving. This could be actually dangerous. But that's my opinion, but I'm sorry, I'm not very familiar with standards on public lighting.
Okay, thank you. We have another question from Pascal. He says that you spoke about common signal on AC networks. Is it somehow normalized, or does each country have its own frequency?
I believe each country has its own system and its own frequency. And to be honest, I know very little about different other countries. In Czechia, even in Czechia, we have several frequencies depending on the region where you are. Like each region has their own different frequency. So as I said, very common frequency is 216.7 hertz. Other frequencies are 900 something hertz. There are like 5 frequencies used in Czechia at least. But there's not a global standard. Each country has its own system.
Vicente, do you have any other question or comment?
Well, I have one comment. It's not actually a question. Last year, we did a research here where we bought, at least 20 different LED retrofit bulb lights, right? And we measure each one of them, flicker, index and the percentage of flicker. And of course, all the values, they were very high, right? As far as I understand from your presentation, I think you have the same problem in Europe, right? There's no standard in place yet. Is that right?
Yes, I'm not aware of any standards that would like we only have recommendation from the IEEE 1789 standard. They give recommendations about the maximum modulation depth or maximum percent flicker for each frequency, but it's just a recommended practice.
So there's no standard yet in Europe as far as
no, I'm not aware of it. No.
Okay.
Okay, so thank you, Vicente, for your participation in this webinar. Thank you very much for sharing your experience and knowledge with us. And also thank you, Leos, for your nice presentation and to share this knowledge about Flickr, that it looks like that it's not very related to electronic development, but the relation is very close. We have to take a deep look in the Flickr problem in order to design our LED drivers. So thank you very much for you too.
Thank you very much. It was nice meeting you, Vincent.
Nice to meet you too, Leos. Thank you very much. Thank you, Marco, for inviting me again.
Thank Marco too.
Okay, and well, this is our last webinar in lighting. Maybe we can have any other speech along this year, but officially this is our last webinar in lighting. So I'd like to thank very much for all the audience of these webinars. And also I'd like to thank the Federal University of Juiz de Fora that they participated in many webinars together with us. Also the IEEE student branch from our university. And also I'd like to tell to everyone that all the webinars are available on YouTube. You just have to access this channel, and we have a playlist dedicated only to these webinars in lighting. We have 15 webinars available to you. So thank you very much for the audience, and thank you, Vicente and Leos.
Thank you.
Thank you. Bye-bye.
Okay, bye-bye. Have a nice weekend.
Thank you.
Thank you too.